Ma'am, you're muted.
Okay, so yesterday we are discussing that the receiver tries to make tau 0 using the code phase feedback control loop. Okay, we call it code phase tracking loop. And then either delta phi is made 0, not exactly 0, it tries to make it almost 0 using carrier phase tracking loop, okay, carrier phase feedback control loop. When it does so, automatically delta FD has to be around 0 because you cannot synchronize the phase without making the Doppler 0. But it is not always possible to make delta phi 0. Okay, then the receiver tries to make delta FD 0, the Doppler error 0. The corresponding loop is called carrier frequency tracking loop. Okay. Now when tau is almost 0 and say delta phi k is almost 0, meaning the replica prompt is almost aligned with the incoming code, and the replica carrier phase is almost synchronized with the incoming carrier, then this becomes almost unity. This is also unity. For prompt, delta will be 0. So when tau is almost 0, R of tau will be almost unity. We are considering only the prompt, in phase prompt correlator. So these are called correlator outputs. Okay. So in phase early correlator, quadrature phase early correlator. So this is one correlator pair. We call it early pair. Okay, this is late pair, and this one is the prompt pair. So at the output of the baseband signal processor, we get three correlator pairs. Okay, early, prompt, and late correlator pairs, and these are sent to the subsequent block called the ranging processor. Now, when tau is almost 0, IP, in IP, R of tau is almost unity. If delta phi is 0, meaning carrier phase tracking is happening, then this is also almost unity. And when this is almost 0, this has to be 0 because we cannot have phase synchronized without Doppler being tracked properly. This term also becomes unity. Since this term is much more significant than the noise term at this point, we considered only this one and take the sign, because this is unity, this is unity, this is unity. This has to be greater than 0. Number of samples, power cannot be negative. So the sign of early prompt, in phase prompt IP will be determined by the data bit, right? So the sign of IP will give the data bits. This is how we can demodulate the navigation data when all the feedback control loops are working properly. Now if delta phi is not 0, meaning carrier phase tracking is not happening, rather carrier frequency tracking is happening, then also there is a way to demodulate the data bit, but it is not as accurate as this one, and we will not consider that in this class. Okay, we will consider data bit demodulation when code and carrier phase tracking are happening. Later we will see that when tau is almost 0 and delta phi k or delta fd are almost delta fd is almost 0, it is possible to find the pseudo range and pseudo range rate measurements. Okay. When delta phi k is almost 0, we can get additional measurements called accumulated delta range, ADR. Some of you must have noticed it in the cell phone measurements, raw data. In addition to pseudo range and pseudo range rate measurements, you probably saw some ADR, accumulated delta range. Accumulated delta range can be obtained when carrier phase tracking is possible. Okay. So using the accumulated delta range, it is possible to find a more accurate range to the satellites. Pseudo range gives range measurements to a satellite, but accumulated delta range gives a more accurate range to a satellite. But it is ambiguous, okay? So the challenge here is to resolve that ambiguity and find the range to a satellite, which is more accurate than the pseudo range. Okay? And these measurements can be obtained only when the replica carrier phase is synchronized with the incoming carrier phase. Otherwise, we do not get. Okay? Otherwise, we will just have to consider the pseudo range and pseudo range rate measurements. We will discuss this again towards the end. Once we understand how the feedback control loops work, we'll come back to this and see how the pseudo range and pseudo range rate measurements are obtained. We'll quickly discuss the navigation data bit demodulation also. But we are not going to consider accumulated delta range in this class. Okay? We will see how pseudo range and pseudo range measurements are obtained once all the feedback control loops are working properly. But for the feedback control loops or the tracking loops to work properly, we should provide some initial guess. Okay. So we need to give an initial guess of the code phase, incoming code phase, and the Doppler. Otherwise, they will not be able to make these terms 0. Okay. This initial guess is provided using acquisition. The block following the baseband signal processor is called ranging processor. The ranging processor performs this acquisition operation to find a course estimate of the code phase and the Doppler, incoming code phase and the Doppler. So basically the receiver has to acquire a satellite first. And acquiring a satellite means finding a course estimate of the code phase and incoming Doppler. Okay. Now when I say code phase, what exactly I mean? See, so this is an incoming chip, right? Now first time when you are trying to acquire a satellite, some point in the code period has come, right? We have a number of chips in a code period. Capital N chips. In case of CA code, we have 1, 0, 2, 3 chips in a code period. First time when the receiver is trying to acquire a satellite, some point in that code period has come, right? And we know how to find the phase of that point. Number of chips since the beginning of the current code period before the current chip plus the fraction of the current chip. If you suppose this point has come and this is some chip in that code period, the phase of that point would be the number of chips preceding this chip and the fraction of the chip starting from its rising edge. This is the rising edge, this is the falling edge. So this is the code phase, and the receiver during acquisition wants to find this code phase. Okay, and then the Doppler. So the objective of the acquisition function is to find a course estimate of the incoming code phase and Doppler. This is a one-time process for each satellite. This is a one-time process. It will acquire the satellite, and then on successful acquisition, the feedback control loops will start operating, meaning tracking will start. Okay, and until the satellite is lost, tracking will continue. Acquisition will not happen again. If the satellite is lost, meaning the receiver cannot make tau 0 or delta phi 0, delta fd 0, then acquisition has to be performed again. But if that does not happen, acquisition will not be performed again. It is just a one-time operation for a new satellite. First time it has to be done. And during this process, a course estimate of CP and FD, the incoming code phase and the Doppler is obtained. Acquisition can be performed either in the time domain or in the frequency domain. Modern receivers perform acquisition in the frequency domain, okay, because it is more computationally efficient and faster. But here we will consider the time domain operation because it is intuitive. So we will understand the time domain operation, how it can be performed in the time domain. But the time domain operation is computationally expensive and not used in modern receivers. Modern receivers use an equivalent frequency domain approach, which is much faster. Okay. So in the time domain, what happens is the receiver, here you see, within a code period, you can pick a number of points. So it can be some point in the first chip, it can be some point in the second chip, and so on. So you can pick a number of points within the code period. So you can assume that the incoming code has started from that point. So this way there will be a number of candidate values for the incoming code phase, right, within a code period. So with these candidate values, you start the code generator. You start generating the prompt code. For different candidate values, you will have different prompt code because you have to start at the corresponding point and then run it. And then you can also have different candidate values for the Doppler. So using those candidate values, you can generate the replica carrier. So this way, for one set of candidate values of the incoming code phase and Doppler, you can have one set of replica carrier and code generated. So using the replica carrier and code generated, you just follow the same process as before and find this prompt, in phase and quadrature phase correlated outputs, IP and QP outputs. So for each candidate values of CP and FD, you will have one set of IP and QP. So like this, you will get many sets of IPs and QPs. Then the amplitude of this correlator pair is generated. So IP square plus QP square and square root of that, which gives the amplitude, is generated for different candidate values of CP and FD. Okay, how will that help? So here I have written the expressions of IP and QP once again. See what happens when we square these terms. If we square I and Q and sum them, we have cos square phi k, sin square phi k. Cos square and the term preceding this cos and sin are the same in both IP and QP. So we have m square root of 2p data bit, autocorrelation function, and the sync function. So this is the same in both I and Q. So if we square these two and sum them, we have cos square plus sin square, so this becomes 1. So we basically eliminate the carrier phase term. And we are left with this square, d square. D can be either plus 1 or minus 1. When we do d square, it is also gone. So we are left with m square into 2p times r square times the whole thing. Right? And then since this is comparatively small, we ignore this in our discussion. Noise will be there. Okay, it will introduce error. But we cannot do anything about it. We just need to take that into account statistically. So ideally, without any noise, the amplitude will be given by m square times 2p times r square before taking square root times r square times this one. And then once you do square root, you get m square root of 2p r of tau times this one. So by squaring them and summing them, we are actually getting rid of the data bit sign, and we are also getting rid of the phase term. Cos and sin also we are eliminating. Now for different candidate values, we will have different amplitudes, right? Now some of the candidate values will be closer to the truth, right? So the set which is closest to the truth will have tau almost 0. Tau is the code phase error, right? Actual code phase minus incoming code phase. So actual code phase minus the receiver's guess of the code phase. So CP minus CP hat is tau. So for the guess or for the candidate CP, which is closest to the truth, we can expect that tau will be almost 0. Similarly, for the candidate Doppler, which is closest to the truth, closest to the incoming Doppler, the actual Doppler of the signal, delta FD will be almost 0. Now we know that when tau is almost 0, R of tau is unity. It has maximum value. Similarly, for the sinc function, when delta FD is almost 0, this is unity. For all other values of tau and delta FD, they will be less than unity. So for the candidate set which is closest to the truth, this amplitude will be maximum, right? So what the receiver does is it considers the maximum amplitude of this, of all the possible candidate values, and compares this against a threshold. This threshold is predetermined. Now, if this maximum amplitude crosses the threshold, it does one more test. It takes the maximum amplitude and the second maximum. So the value which is maximum after this maximum value, the second maximum, and finds the ratio of the maximum amplitude to the second maximum. If that ratio is greater than some predetermined value, if both the tests, the maximum amplitude crossing the threshold and the ratio of the maximum to second maximum is greater than predetermined value, if both happen, then the receiver declares that acquisition is successful, meaning it has been able to find a valid guess of CP and FD, incoming code phase and FD. In other words, it is able to acquire the satellite. Okay? This is called successful acquisition. Now you understand why the first test is done. Maximum amplitude is checked against a threshold. The second test is done to avoid false acquisition. So when the peak occurs, the second maximum has to be a bit away from the first. If both are similar in magnitude, then this is not correct. Then there is something wrong. Okay. If everything is okay, the ratio between the maximum peak and the second maximum should be greater than some predetermined value. So when both the tests pass, the receiver says acquisition is successful. It has been able to acquire the satellite. And this guess of CP, the candidate set for which the maximum was obtained was is taken as the guess for the code phase and FD. Here we see the acquisition result of a real receiver. This plot shows the acquisition result of a real receiver. Okay, this peak is what we want. This blue peak is what we want. What is plotted here? Here, for different candidate values of the Doppler frequencies along this axis and different candidate values of the incoming code phase, the correlation amplitude is plotted along the z direction. You just see for some candidate values, we get the blue peak. Other candidate sets, we just have some small peaks because of noise, okay? We get this red surface because of noise and some small values of this. When we say that the code phase should be generated for different points, what should be the step size? How can we increment the code phase to generate different candidate values? Generally, these candidate values are incremented in steps of 0.5 chips, meaning within a chip you get 2 points. But a receiver can also generate these candidate values with finer steps. So if you consider 0.5 chip step size and there are 1023 chips, within a chip you get 2 points. If there are 1023 chips, you will get 1023 into 2 points. This many candidate values of CP. In this particular case, the receiver generated this candidate values with a finer step, most probably with 0.1 chips. So 0.1 chips means within a chip, you get 10 points, 10 different candidate values. Each point will have a corresponding code phase, right? So you get 10 points means you get 10 different candidate values of CP. And there are 1023 chips. You need to do this over a code period. A code period is also called code epoch. Okay. So over a code period or a code epoch, you need to do this. Each chip will give, if the step size is 0.1 chips, each chip will give 10 points. So 1023 chips will give 1023 into 10 points, those many points. So most probably in this case, the receiver used 0.1 chip step size, and while plotting it zoomed the portion near the peak. Okay, so these are the number. Those many points are considered, their code phases were taken, so you get the number along this direction, number of points. Now along this direction, different candidate values of the Doppler is plotted. Generally, Doppler is changed in steps of 100 Hz. Okay, the receiver can also choose to select a finer step size less than 100 Hz, but generally 100 Hz step size is chosen. It is not clear what step size they have taken to generate the plot, but it will be on that order. Okay. So the blue peak here corresponds to some number, which we can find from this axis, and that point will give the corresponding code phase, and that code phase will be taken as the guess. Similarly, along this axis we will find the corresponding Doppler, and that Doppler will be taken as the guess. So this way, using acquisition, we can find a coarse estimate of the incoming code phase and Doppler. Okay. Although we did not discuss the frequency domain operation, it is actually equivalent to the time domain operations. All these different amplitudes are generated equivalently in the frequency domain, and the frequency domain operation is much faster. Okay. Any question? If there is something that you did not follow in acquisition, ask me at this point. Okay, fine. We are discussing the ranging processor. We have already talked about acquisition. Next, we will talk about tracking loops. We'll talk about the code phase tracking and carrier frequency or phase tracking in more detail. And then finally, we'll see how navigation measurements can be generated. Navigation measurements mean pseudo-range rate measurements, and navigation data. Okay, the same thing that we discussed just now is shown here. So we'll skip this because we have already discussed acquisition. In the previous presentation, we talked about the left part, which is the baseband signal processor. We discussed carrier wipe off, we discussed code wipe off. Now, the right side of this block diagram shows the ranging processor. The right side actually closes the feedback control loop. So this is the feedback path. Similarly, here also this is the feedback path. We discussed that the code phase tracking loop tries to make tau 0, and it uses early and late correlated pairs from the baseband signal processor, whereas the carrier tracking loop tries to make delta phi or delta FD 0 using a corresponding feedback control loop. It takes the prompt correlated pair as input. So again, the definition of code phase is given here. So let's say the black one is the incoming code, and the green one is the prompt code generated by the receiver. So at some point P, what is the code phase? This line on the left side shows the beginning of the current code epoch or code period. So what is the phase of point P? Code phase of point P is the number of chips preceding this chip, current chip. Let's denote that as N. N is the number of chips preceding the current chip, and TC is the chip width, so N times TC, and then the fraction of the current chip up to this point. So A is that fraction, it is within 0 and 1. A is that fraction, A times TC. So if TC is in seconds, the duration of the chip is in seconds, this code phase is in seconds. We can also represent TC in chips. In that case, TC is just 1, and then the corresponding code phase of this point will be in chips. So it's possible to represent code phase in both seconds and chips. Now just see the code phase of P in the incoming code. This is the value of A for the incoming code. For green, the replica prompt code, this is the value of A. A is not the same for black and green unless green coincides with black. When green occurs differently, it is shifted. A will not be the same for both. And how much is the code phase error? This is the code phase error. We just consider the rising edge of black and rising edge of green, and the difference between the two is the code phase error or tau. Making tau 0 means you are actually trying to align green with black. What is the order of tau after acquisition? Now, since we have considered a step size for different candidate values of CP within a chip, say 0.5 chips, tau is within a chip, actually within 0.5 chip after acquisition. This error is of the order of 0.5 chips with less than 0.5 chips after acquisition. This is not sufficient. So this has to be reduced. And also this can change over time. Right? So we need to continuously try to make this difference 0. It is no longer a one-time process now. This has to be done continuously in time. And that is what the code phase tracking loop tries to do. Continuously it tries to make tau 0. Okay. The code phase generator, once acquisition is successful, is started with the corresponding candidate value of CP. The candidate value of CP which gave the maximum correlation amplitude is taken and used to start the code generator once acquisition is successful. Similarly, the candidate value of the Doppler corresponding to the maximum is taken and used to generate the replica carrier here. This is how we use the values that we got from acquisition. In the ranging processor, acquisition block also lies, which is not shown because here our focus is tracking. But in the first block diagram where I showed all the primary components of a receiver, ranging processor has both acquisition and tracking. Okay. Here acquisition is not shown, but acquisition also resides in the ranging processor. Similarly, for the carrier, let's say the red is the incoming carrier after down conversion. Its frequency has been down converted to megahertz. The incoming frequency was in gigahertz. It has been down converted to megahertz, but that does not change the Doppler. Doppler remains the same as in the incoming signal. And what is the order of Doppler? In case of GPS, Doppler is within plus minus 10 kilohertz. Okay. The down converted intermediate frequency will be few megahertz, and Doppler is within plus minus 10 kilohertz in case of GPS L1. We are considering GPS L1 carrier. For IRNSS L5, the range is little less because the carrier frequency is less. It will be within plus minus 8 kilohertz. For S band, where the carrier frequency is more, almost twice, the range of Doppler will be around plus minus 15 kilohertz. Because if you consider the Doppler expression there, in the numerator you have the carrier frequency. So higher the carrier frequency, more will be the Doppler. Okay. So the range of Doppler is within few tens of kilohertz. For GPS within GPS L1 within plus minus 10 kilohertz. For IRNSS L5 within plus minus 8 kilohertz in that range. For IRNSS S, it will be more than that. Now, when the receiver attempts to do carrier phase tracking, attempts to make delta phi 0, blue here is the replica carrier. Blue will be aligned with red. It will be phase synchronized. So you will not be able to see red and blue separately. When it tries to make delta phi 0 using the carrier tracking loop. If it cannot make delta phi 0, it will try to make delta FD 0, Doppler error 0. Then the frequency of red and blue will be the same, but they will not be phase synchronized. There will be a constant phase offset. That offset will not change because you are correctly finding the Doppler, and the down converted frequency is known. FIF is known. Total frequency is FIF plus FD. So if you can correctly find the Doppler, which is the unknown component, you are actually getting the frequency, carrier frequency. But phase will not be synchronized. There will be an offset between red and blue. If carrier frequency is tracked, if delta FD is made 0, not delta phi, there will be a constant phase offset, but both will have the same frequency. The code phase tracking loop or code tracking loop is also called delay lock loop. Okay. And its objective is to try to zero the error between the incoming code phase and that of the receiver generated replica code. Tau is nothing but the difference. Tau is Cp minus Cp hat. Cp is the incoming code phase and Cp hat is the guess or the receiver's knowledge of the incoming code phase, basically the prompt code phase. So it tries to make tau 0. And to do that, it uses a nonlinear function called a discriminator, code phase discriminator. A discriminator is followed by a filter, okay, it's called loop filter, and another block called code numerically controlled oscillator, NCO. Okay. Similarly, the carrier tracking loop tries to zero the error between the incoming carrier phase or carrier Doppler, either it will be carrier phase or carrier Doppler of a visible satellite and that generated by the receiver. When it tries to zero the phase, it will be the phase error, the difference between the incoming carrier phase and the carrier phase of the replica. If it is Doppler, then the difference between the carrier Doppler, the actual Doppler, and the receiver Doppler of the receiver. So that difference will be considered. When it tries to make delta phi 0, the corresponding loop is called a phase log loop, PLL. When it tries to make delta FD 0, the corresponding loop is called FLL, frequency logged loop. So I can synonymously say DLL, PLL, FLL. So DLL is nothing but the code phase tracking loop. Since we are trying to track the incoming code phase or incoming Doppler or incoming carrier phase, we call these feedback control loops tracking loops. So in place of code phase tracking loop, I can simply say delay lock loop or DLL. Similarly, in place of the carrier phase tracking loop, I can just say a PLL, phase lock loop. And the corresponding term for the frequency loop is the frequency logged loop. The carrier tracking loop also has a discriminator. If it is carrier phase tracking, the discriminator is carrier phase discriminator. If it is carrier frequency or Doppler tracking, then the corresponding discriminator is called carrier frequency discriminator, which is followed by a loop filter and then the corresponding carrier numerically controlled oscillator. So these are different components of the loops. In the next few slides, what we will be doing is, first we'll try to understand the operations of the discriminators. Why we have these nonlinear functions here. Port phase discriminator and carrier phase or frequency discriminator. We can also call them DLL discriminator, and then here PLL or FLL discriminator. From the name you have to understand which tracking loop we are considering, whether it is port phase tracking or carrier phase or carrier frequency tracking. We will first understand the objectives of the discriminators, why we have these nonlinear functions in place. Then we will understand the operating principles of the port NCO and carrier NCO. Note that port and carrier NCOs are part of the baseband signal processor, but they close the loop. That's why I have shown them here. So we'll understand how these numerically controlled oscillators work. And then under some assumptions, we will transform these feedback control loops to a block diagram representation, okay, with corresponding transfer functions. So we'll basically have some transfer function and block diagram, simplified block diagram of these feedback control loops under some assumptions. And then in that feedback control loop with transfer function representation, we'll understand the operating principles of the loop filter at a top level, of course. Okay. Once we do all this, we'll understand how the feedback control loops work, how the tracking loops work, and then we'll see how the navigation measurements can be generated. So this is the roadmap. This is what we are going to do. Part of it we will be doing today, and then we'll continue in the next class. So in the next class, we are going to discuss all this, and then the only thing that will be remaining is the navigation processor. Once we complete all this one, tracking and navigation data, navigation measurements generation, we'll quickly talk about the navigation processor. The navigation processor uses weighted least squares or Kalman filter. Okay, we are not going to talk about the operating principles of weighted least squares or Kalman filter. We'll just see how they can be implemented within a receiver, GNSS receiver, and that will close the discussion. We'll not have any class next week. Tomorrow is the last class, and your test is on 7th April. I already sent you an email. Test is on 7th April. Marks for the test would be 30. So it has 30% weight, and duration is from 8 to 9:30 a.m. 1.5 hours test will be held online. I'll send you another email giving all the instructions for the test. So let's consider the discriminators, why we have these nonlinear functions. The discriminators are nonlinear functions, as we know, of the in-phase and quadrature phase correlators. And their objective is to extract either tau or delta FD or delta phi. Here we see the expressions of the correlators, in phase, quadrature phase, either E or P or L, early, prompt or late. This bar shows OR, okay. In the previous representation I wrote OR, here I just put bar, they are synonymous. Depending on the value of delta, we can have E, P or L. So when we have P, delta is 0. When we have E, delta is minus D by 2. D is the early late correlator spacing. And L will have delta plus d by 2. We already discussed this in the previous presentation. Now see, these correlators are actually nonlinear functions of tau, delta fd and delta phi k. So if you want to extract these quantities from these nonlinear expressions, we need a nonlinear function. A DLL discriminator is basically a code phase discriminator. Its objective is to extract tau. Okay, and it uses early and late pairs. So we'll write the DLL discriminators considering early and late pairs. For the carrier frequency or carrier phase discriminators, we consider only the prompt pair, prompt IP and QP. So using IP and QP, the prompt correlators will have the carrier frequency or carrier phase discriminator. Here we see the discriminator outputs. Along x-axis we have the actual tau. So there must be some actual tau, the actual error, Cp minus Cp hat. The discriminator is actually finding a value of that actual tau. So along the y-axis we have the discriminator outputs. And on the left you can see some discriminator functions. Except for this one and this one, generally we use early and late correlator pairs to implement the discriminator. There are some exceptions where we also consider the prompt, but generally we do not. That's why I did not show on that block diagram. Okay. So some functions have been given so that you understand how they look. So what you have to do is you just need to use these expressions here and do some simplification. Consider the first order term because there will be higher order terms. So you just consider the first order terms and you will find that this function will be, you will get tau here. Okay, so once you substitute for all the correlator expressions I and Q and do the math, do some algebraic simplification, you will find that tau appears in the final expression. And the output is plotted here for different discriminators. If you notice carefully, you will find that there is a region where the outputs are linearly related to the inputs. So this region. Over this, the output is linearly related to the input. And actually, we want to operate in this linear region. Okay. But if you consider this side also, it is possible to operate. It is just that the function will not be linear. It will be non-linear. So although this is a nonlinear operation, we can find a region where this can be approximated to be linear. Outside that region, it will be nonlinear. Now, there is some tau, actual tau. Discriminator is giving some value of that, which we get from the y-axis. For a given tau along the x-axis, we get the corresponding value from the y-axis. Discriminator is giving that as the value of actual tau. What does the feedback control loop do? It is a negative feedback control loop. So it tries to do some corrections in the opposite direction. So for a given tau, the discriminator here will give some output that will be taken as the error in the loop, and the loop will try to correct it through negative feedback control. When that happens, eventually tau will reduce, and the objective is to bring it here. So let's say after acquisition, tau was somewhere here. Then the tracking loop will try to bring tau here through negative feedback control. Now this region where the tracking loop can pull tau to 0 is called the pull-in region. Pull-in region. So within this region, the feedback control loop can work properly and bring tau to 0. Outside the pull-in region, this will not happen. For example, suppose we have a discriminator where for positive tau, the discriminator gives a negative value. Actual tau is positive, but the discriminator gives a negative value. Then what will happen? The loop will assume that the error is negative, although the actual error is positive. And assuming a negative error, it will try to take some corrective action. In the process, it will actually go away because the positive error is considered as negative. So outside the pull-in region, there is no guarantee that the feedback control loop will bring tau to 0. This will happen only within the pull-in region. Okay? This will be clear to you once we talked about the FLL discriminator. In the carrier frequency discriminator, we can show what happens when the error is outside the pull-in region. So here we see different FLL discriminator outputs. Along the x-axis, we have the actual Doppler error, delta FD. Along the y-axis, we see the discriminator outputs. And just like the DLL discriminator, here also we have different types of discriminators, different nonlinear functions. One such discriminator is called ATAN2. So it uses the ATAN2, the 4-quadrant arctangent operations on the prompt correlator pairs. So ATAN2 discriminator considers two correlator pairs. So this pair is generated at the current step, and this pair was generated in the previous step. Now we know that each pair is generated over a coherent integration time, which is between 1 millisecond and 20 milliseconds. Here we see the outputs for 10 millisecond coherent integration time. All the outputs shown here are corresponding to 10 millisecond coherent integration time. So to find the final expression, you need to substitute for I and Q. Here we have the expressions of I and Q, and do the math. Simplify things further and you will find that in the resulting expression delta FD appears. And the outputs are plotted here. But to plot these outputs, we have not considered the effects of noise. Okay, these are all clean outputs, assuming there is no noise. So you ignore noise and plot the outputs. So this solid line shows the FLL discriminator output when we consider the ATAN2. In place of ATAN2, we can consider ATAN, 2-quadrant arctangent operation. Then we'll get this dashed line. One more discriminator is shown, which is called cross product discriminator, and the expression is given here. The dotted line here shows the output for the cross product discriminator. So these are different FLL discriminators, different nonlinear functions. For the A-tan2 discriminator, this is the linear range. For A-tan, we have half of that. The linear range is reduced. For cross product also, the linear range is less. The pull-in range for the A-tan2 is this one. The entire linear range is the pull-in range. For A-tan, which is the dashed line, the pull-in range is this much. Here, it will not come to 0. So if delta FD is here, the output is also positive. Actual error is positive, output is also positive. The loop will take corrective action and try to bring delta FD 0. But if it operates here, if delta FD is here, actual error is positive, but the discriminator output will be negative. So what the loop will do, it will take corrective action, it will increase and it will come here. This is called false lock. Here you see clearly, if the error is outside the pull-in range, the error will not be reduced to 0 through feedback control. Rather, we'll have false lock. It will go to a wrong value completely. We'll continue tomorrow. Any question? Fine. If you have no question, you can leave. But if you do not understand something, you can ask me tomorrow. Yes. Sujit, you want to say anything?